Okay, so we are on now. And yesterday we started discussing this notion of stability of fixed points of dynamical systems, which is a crucial notion because we don't just care about what initial conditions which are initialized at a fixed point too, which is what we know, they just stay there, but also what neighboring trajectories do, whether they approach the fixed point, they stay in a neighborhood of fixed point, or they probably go away from them. So that's what brought us to this notion of stability, and we tried to make it more precise. And there were two definitions that we saw yesterday, starting with the definition of Lyapunov stability, where we said that in some sense, this was the notion that neighboring trajectories would be confined to an epsilon ball around the fixed point. And for every epsilon ball that is given to us, we would be able to find a smaller initialization radius, a delta ball, in which no matter what initial condition I choose, it would forever stay inside the epsilon, the ball radius, right? So this was, so to speak, the Lyapunov stability that we saw yesterday. We saw an example of the pendulum where we discussed why these two numbers, epsilon and delta, should be different, because it's you need that difference, because it's not necessary that you can just you always, at least in this case, you have elliptical orbits, so you would not be able to always come up with a single radius in which you can always confine your solutions, right? So that's why two different radii are needed, one for confinement and one for initialization. And then we saw the notion of asymptotic stability, where we not only want our solutions to be confined to nearby trajectories, to be confined to a fixed point, a neighborhood of fixed point, but also to be approaching towards it asymptotically. So for that, the first thing we require is that it should be stable in the sense of Lyapunov, but also we should have potentially a smaller initialization radius, delta naught, such that if we initialize trajectories in that radius, then not only will they stay confined to the epsilon neighborhood, but eventually they would go towards the fixed point. As t tends to infinity, they would be approaching the fixed point. So this was a third radius that was required in this case to define asymptotic stability. And because of due to that, there was a domain of attraction that came in, which is basically the set of all points, initial points, for which the trajectories are decaying towards the origin, which was our fixed point, without any loss of generality. And then we saw this damped pendulum example, which is where the origin is asymptotically stable due to energy considerations. We first wrote down mechanical energy of the system, and we saw that the rate of change of energy is non-positive. So because we have a positive damping, it's always it's always non-increasing. And we were using the phase portrait, or not really the phase portrait, the level curves of the energy in the phase space. These are the level curves, which are elliptical. Mind you, these coincided with the trajectories of the dynamical system in the undamped case. These are no longer the trajectories, but still we can define an energy as we did in the damped case as well, and draw its level curves. And we were seeing, since the energy is decreasing, we inferred that by smooth dependence of solutions, that in general trajectories would be decaying. And then we use the Lassalle's invariance principle that although they are decaying towards lower and lower energy surfaces, they should eventually be leading towards the only full trajectory which is contained on this line, which is the origin itself. So that's how we concluded that in the end, we would spiral down into the origin. Just merely trajectories decaying towards lower energy surface does not guarantee us that they are going towards the fixed point. And this is how we were able to show that indeed, in this damped pendulum case, the Lassalle's invariance principle allows us to show that the origin is a asymptotically stable fixed point, right? So let me see if I said everything. Yeah, so just to quickly recall, the idea was that you should be able to find a scalar function, which is smooth. Lassalle's invariant principle says that if you're in a set U and we find a scalar function, which is C1, and it is decreasing or non-increasing rate in over this set, over the solution trajectories, which is the case with energy, as we saw yesterday, and also all the points on which this function V dot vanishes, that's the set I. The fixed point is, if there is a fixed point in this dynamical system, it should also be contained in this set. So in our example, this red line, which is the set of vanishing velocities, is the set I. It contains the fixed point. And in this case, when this applies, we were able to, that's what the Lassalle's invariant principle says, that the set of accumulation points or limit points of all the trajectories that stay in U forever is contained in the set I. So it should be contained in the set I, and is basically precisely contained in the set of full trajectories in set I, and the only full trajectory in set I is the fixed point itself. We do know that the level curves are decreasing, are going towards a lower energy level. So they are perpetually monotonically decreasing. Instantaneously, they're not, but in general, they're decreasing. So they're accumulating towards a point. The only point they can accumulate towards is the fixed point, which is the only full trajectory in set I. So this is what we saw yesterday. It was a general picture that we drew. This is the set U, which contains all trajectories, and there would be a set I in it, which is the set on which V dot is 0. Within that set, there could be in general some blue full trajectory to which all trajectories would be accumulating that stay in U, right? So that's the general picture. In our case, this blue trajectory happens to be the fixed point. So, and yesterday, basically, we started discussing this example where, which I had just introduced, in polar coordinates is the radius r, r dot is r times 1 minus r, and theta dot is sine squared theta by 2. And we were trying to see, just to recall, that this first equation, both of these equations are decoupled from each other, so they can be viewed as one-dimensional dynamical systems in themselves. And we saw that the first equation is r dot equals r times 1 minus r, already has two fixed points that we can analyze, 0 and 1. And this is a one-dimensional system, so we already have tools to I drew the graph of this function yesterday. Somehow it disappeared. Let me draw it again. So the idea was that this would be an inverted parabola like this, with the fixed points 0 and 1. When it's positive, we know that r would be increasing. This is what we saw in initial lectures and where we discussed one-dimensional dynamical systems, and it would be decreasing whenever the graph is below the x-axis. So when r dot is negative, right? So that's how we know that 0 and 1 are fixed points, and this is the flow that we would have away from the origin, right? So before, I think this is where we stopped yesterday. Are there any questions about the material so far? I think I always miss questions in the chat. Okay. Just check, there are no questions in the chat either. So let's continue. As I was saying yesterday, that this is a very nice setting because these two equations are simple, they're decoupled from each other. We found two fixed points. And if we now go back to Cartesian coordinates, say X and Y, and I screwed up yesterday in trying to draw the circle, so I'm prepared today. I started with a nice circle, which corresponds to radius 1. And so even though it's a single point in this on this axis, it corresponds to an entire unit circle in Cartesian coordinates, right? And similarly, theta describes polar angles. Say we define theta as increasing in anti-clockwise direction as we go measured from the x-axis. So this would tell us coordinates of every point on this Cartesian 2D plane. So what we know in general is that r equals 1 is a fixed point. So if we start on r equals 1, then we stay on r equals 1, right? So in other words, it's an invariant set. So anything that starts on this unit circle will always stay on this unit circle in the Cartesian plane. So we'll just quickly write it down. So what does it mean? Intuitively, it means that if we start on it, it means we stay on it. Right, so that's about R. And what about, we have the second equation that we did not pay attention to. It's sine squared theta by 2 because it is a square. We know that this would always be non-negative. So does it have any fixed points? Yes, it does. Namely, theta equals pi, sorry, not pi, because if we substitute theta equals pi in here, we get sine squared pi over 2, which is 1. So that's not a fixed point. Apologies. It's actually 0, right? So theta equals 0 is a fixed point. And what does theta equal to 0 correspond to on this Cartesian plane? Basically corresponds to the positive half of the x-axis, right? So this, the negative half would be theta equals pi, so positive half is basically theta equals 0. And this is another invariant set, because again, it doesn't matter what r is on it. Whatever r is, if we start on it, we stay on it, right? So I will just add theta equals 0, comma r equals 1, r invariant sets. And now, if we try to draw the phase portrait of this, we kind of know what happens here in general when so these two equations are decoupled. As I said, r equal 1 is an invariant set. Whenever theta is away from 0, it is theta dot is increasing, right? Whenever it's non-zero, it's increasing. So the only so what we know is that how is the trajectory behaving on this unit circle? It's increasing. So theta, in general, the flow would be in this direction for any theta which is non-zero. So we expect that the trajectory here would be doing something like this. And there are two fixed points for r equals. So r equals 0 is a fixed point, first of all, which corresponds to this point. And r equals 1 is also is an invariant set on this plane. But if we look at the intersection of these two invariant sets, that gives us a unique point. This gives us another fixed point. So these two are fixed points of the two-dimensional dynamical system now, right? And so, and we already know that when when theta is fixed, when theta is not varying, namely on this blue line, so theta is fixed, R would behave according to this one-dimensional dynamical system that we drew. So basically, we would be getting the same dynamics here if R is between 0 and 1. So this is 1. Then we would be increasing towards this fixed point. So we already know what we are doing, at least in some region. And now we can try to infer what the rest of the trajectories would be doing in the phase space. We know that at this point, we would, of course, be fixed. But in general, this gives us basically 2 points to consider here. We see that whenever R is more than 1, it would be decreasing towards 1. And whenever R is less than 1, it would be increasing towards 1, as we see in this graph. When it's more than 1, we decrease towards it, less than 1, we increase towards it. And in general, in the second thing to consider is that theta, while we are doing that, and we would basically be always approaching the unit circle, except if we start on the origin, which is where we stay fixed. R is 0, it's also a fixed point. In general, we would be approaching the unit circle, but how are we approaching it? Theta would also be changing in general. The only way theta can change away from this line is that it would only be increasing. So in some sense, we would be rotating in this direction. So if we take these, put these two facts together, generally we would get a trajectory which is sort of, decreasing, but at the same time, this angle is increasing. So it would be only going in, and it would be approaching towards this unit circle. But now it cannot really cross this line because it's a trajectory in itself. So we have to respect uniqueness of solutions. So basically it would be approaching towards this fixed point, right? So this is what we can expect to be doing. And similarly, if we start on any trajectory in inside the circle, we expect that basically this is what would be happening. We would be approaching towards this unit circle, and ever so slightly, we would keep increasing theta. And again, we cannot hit the fixed point here, but we cannot cross this line because we have to, again, respect uniqueness of solutions here, but we would be kind of going in this direction. So all trajectories would sort of be doing this counterclockwise direction while increasing radius towards 1. So this is how, in general, trajectories we can just start script. Oh wow, automatic recognition. Help here. So yeah, so ultimately what we are seeing from this picture is that basically all these trajectories, whether we start inside or outside, they're ultimately leading to this fixed point, right? This single point here. So this is a very nice thing because everything seems to be leading towards this fixed point. Ultimately, everything is decaying towards it. Can we call this fixed point a stable or asymptotically stable fixed point? But because everything seems to be going there, at least if we focus on a small neighborhood, right? It just happened. Okay. Sorry for that. And so at least if we focus on a small neighborhood, such as here, what we are seeing is that everything, maybe things are going away for some time. maybe trajectories are leaving for a little bit, as we see maybe in this region, but ultimately they would circle back and come back here through this route, right? And unless you're starting at r equals 0, everything else basically seems to be coming towards this fixed point. So it's really attracting not just neighboring trajectories ultimately, but also trajectories from all through the phase space except the one starting at origin. So can we call this a stable fixed point? Let's forget about, or asymptotically stable fixed point. Let's forget about the definition for a minute. Is this a behavior that one would expect to see if we are talking about stability? Right. So my guess would be, I mean, you wouldn't want this to happen, because yeah, ultimately you are coming here, but you're also leaving, no matter how small a neighborhood I consider. Look at what is happening here. We are also leaving this neighborhood. No matter, we can never confine our solutions in a small neighborhood of this fixed point, right? So this is to say, I remember Professor Haller used a couple of years ago. I think I was sitting in this lecture when he was presenting this example. He had a funny take on it. It's kind of like, I wouldn't want my turbine foundation to be described by this equation, right? Because, or this fixed point, because it sort of tells me that, yeah, ultimately my turbine would always be stable and everything would come back to the foundation after the turbine ends up destroying the whole building and goes out and ends up coming back, right? You don't want that's not really a stable design, seems like. So that's something, I don't know how much the material stayed on with me, but at least that analogy stayed on with me. So I think I thought it's worth recalling that. So the idea is that, of course, from our intuitive understanding of stability, this does not cut through for it to be a stable fixed point. And indeed, if we look at the definition as well, this is not stable, because no matter how small an initial radius I consider, delta naught, delta, there are some trajectories that if we initialize in them, they end up leaving an epsilon ball. You would never be able to confine them in an epsilon ball, right? So any trajectory which is initialized in this region, no matter how close you initialize it to the fixed point, they would end up leaving an epsilon ball. And remember, the definition of stability was that for every epsilon ball, we should be able to find an initialization radius such that any initialization condition in that radius does not leave the epsilon ball. So stability is a must. You should be confined first, and then you start decaying. That's what guarantees asymptotic stability to us. So we'll just big description for to make this point that fixed point P on this point P is not stable. So this means that it cannot be asymptotically stable. Again, even though these definitions sound all mathematical, they are trying to make precise things or ideas that we very realistically and physically expect from systems. So there's a lot of value in that. And what, just a side note here as well, that P is actually an attractor. which is so there exists an open domain in which it is attracting trajectories. So I think I mentioned invariant sets here in sort of an intuitive setting. So it would help also to write down a formal definition of it. There's all sorts of invariant sets, but so you could have forward invariance and so positive invariance or backward invariance in time, but what is most frequently used is just invariance in all for all possible time values. So set S in the phase space is invariant for a flow map FT, which maps our, for any map actually we can define an invariant set, which in our case what makes sense is to define it for the flow map, which maps initial conditions to final positions in phase space. So a set S is called invariant for this map, flow map, if it satisfies f of t. If we apply the flow map to this set, we get the set back, right, for every time. Okay, so let's quickly, so we've so far been discussing what is stable, and we saw an example as to what that something that is not stable. Perhaps it would also be useful to have a definition for instability, right? So we have some intuition already that if there are some trajectories which are leaving an open neighborhood of a fixed point, then it is not a stable fixed point. So let's try to also formalize it. So x equals 0 is unstable if, well, as I said, it's unstable if it is not stable. It's as simple as that. So what does it, I mean, if I'm kind of cutting corners here by just saying now it's that's what it makes sense. But remember, when we had defined stability, we had a mathematical definition for it using epsilon and deltas. If we want to, this is a mathematical definition because I'm saying that if it is not stable, so everything that is stable, we negate that, and that's how we get something that is unstable. So how do we mathematically negate that? So remember, I will just quickly recall the definition of stability. So we said that for every initialization time t naught in R, there exists, I'm sorry, and for every epsilon confinement radius that we provide, there exists a delta radius of initial conditions, which potentially depends on epsilon as well as t naught. such that for every x naught initial condition in which is inside this initialization radius, we have the solution xt starting from this any initialization point in this radius would be confined to epsilon, right? So how do we negate this statement? I mean, the side remark is just that on negation, this is really a trick when you have so many, so many of these symbols for every, and there exists. Usually, if you want to negate for every, if it means that for everything this should, for every such case this should hold, it means that the opposite would be for some case it does not hold. So it means there should exist some case in which this is not true. And so if we want to negate for every, usually we use the symbol that there exists. And if there exists some case in which something is not true, if we want to negate that statement, then we would say for every case, it is true. If it is true for some case, it means that it should be not true for every case. So in the negative of that, that's what we would have. And if I try to apply these rules, the way would be that there should be a time instant t naught. There should exist an initialization time, and there should exist some radius beyond which I'm not able to control. There would be some radius such that solutions would always go outside, such that no matter how small I start initializing my trajectories, there would be one initial condition in that radius such that the trajectories would leave that epsilon form, right? So this would basically be the mathematical definition of instability. So no matter how much I try to restrict myself close to the equilibrium point. So this is what the initialization radius is. After some time t naught, after some time, I think there was I forgot to write here that this should hold for every t in stability. But here, when we negate it, it again means that for some t, this should be true. So if I'm trying to negate it, then this would mean that I say here for some t. So no matter how close I start at the origin, there would be some epsilon ball that I would be escaping after some time, right? So the usual picture that goes here is that as we drew in the other case, once again, time is on this axis, and what we are saying is that no matter how close we start near the fixed point, there would be some epsilon. So this is the delta radius of initialization, consistent with the colors. So no matter how small I pick delta, there would be some epsilon such that, and there would be some some particular trajectory, at least one, is that if I start here, then I might stay in the red ball, I might stay in also the blue ball for a while, but there would be a time after which I escape both of them. So this happens for some t greater than t. So there exists a t greater than t naught such that your solutions would start going away. And you might say that, well, that's okay. Maybe there's just one trajectory which is doing that, but in general we are probably staying bounded, right? So what's the problem? No, but the problem is that we have smooth dependence on initial conditions. So the moment I found one trajectory which is doing it, there would be an entire open set of trajectories which would be also doing that. They might be doing it at some other point, but there would be a number of trajectories which would be doing this, which is getting out of an epsilon. It might be doing that for some other epsilon radius, but there would be this happening. So what I'm trying to say is that by the continuous dependence on initial conditions, sufficiently close initial conditions, x zeros, will also give trajectories leaving p epsilon. So what this means is that this is not just one trajectory. This is an open set of trajectories, something that you can measure, and there would be this would be a general observable trend. So this is something that actually leads to observability. This is what leads to our turbine destroying the building. So that there would be observable scenarios in which that would happen. So one final example of this, and what better to look at than our good old pendulum. Unless, of course, there are questions. Okay, if not, then
I have a question.
Yeah, please.
Yeah, you mentioned that the trajectories don't ever touch that point P because to respect the uniqueness of the solution, right? And I was wondering, for the example of the damped pendulum, do they ever touch the origin or not?
So for the example of the damped pendulum, so here I was saying that they never, of course, we have to respect uniqueness. So we always asymptotically end up approaching this point, but never actually reaching it in any finite time. So you're talking about the pendulum here.
Yes.
So
Is it also the case that they
yes,
never...
that's indeed. So the uniqueness of solutions always applies if we have Lipschitz continuity of the right-hand side, which is the case for the pendulum. It would always be spiraling inwards. The trajectories, as we know, usually spiral inwards, but it would take them an infinite amount of time to reach there. So it might be counter to our observation that we let our pendulum go, and then after a while it kind of stops. But there's still microscopic oscillations that we are not able to observe. They're in principle, they're going on. It's going on forever, and it's getting there ever so. It does so very quickly because it's an exponential decay that happens. But yeah, in any finite time, we won't be able to see it reach there. So that's the idea, indeed. It's a good point. Any other questions? Okay. So once again, we were looking at the pendulum. We know that the origin is stable, but there's another fixed point, remember, which is the upright position, x equals pi. So we saw so we don't even need to consider the damped version, or even if we consider the undamped one, we have this fixed point. In both the cases. So this is the origin and this is pi. And usually what we see here is this kind of behavior. So trajectories are sort of approaching this fixed point in one direction, leaving in another direction. And as you would recall, you drew the phase portraits, general trajectories are doing this kind of here. For the undamped pendulum, at least, right? So once again, we don't really need to do much here, in the sense that even if I seem to be no matter how close I am to this fixed point, right, I can consider a delta neighborhood around it. So what color did I pick for it? It's red. I do see there is one particular trajectory, which is if I start initialize here, I'm approaching the fixed point. If I zoom in, I'm approaching the fixed point here, but there's a whole set of trajectories which are also leaving like this. There are trajectories also that come in and then leave. So if I initialize, say, at most of the points, actually, here, 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 it seems that what I'm doing is that I'm leaving an epsilon ball that I can construct. So let's call this. There is an epsilon ball that I would leave for a number of trajectories here. And there's only very particular trajectories, namely on these halves of separatrices, if we initialize here, this is where we seem to be actually converging towards the fixed point. Right? So it's only, if I were to summarize, it's only these initial conditions that stay in the epsilon for all times. All others in this delta ball are actually after a finite time t, which we can even see, they would be leaving this epsilon ball. So in this case, actually, this is again an instance of this is actually, even though there are some trajectories which are, or so many initial conditions which are leading towards the fixed point, we only need one or an observable set to guarantee observability. Even if we found one, it means we have found an observable set. And in this case, actually, it's almost everything which is doing that. And this is precisely the reason you can imagine that why that upright position is called unstable. It's so difficult to land up on that on that position. You need to give a very precisely calculated velocity and to make sure that you land up there. And then also if you let it be microscopic oscillations, the slightest of disturbance would make it go away from there. So this is what this is actually very atypical behavior. So in other words, unobservable. With that, I think this was the final example I wanted to discuss with this first subsection of definitions that we were looking at for stability and finally of instability as well. Unless there are questions, I would like to move on to the next section, which is what I promised yesterday. If you've been looking at what are the notions of stability and how to mathematically define them, so we can actually build systems and do analysis of various systems, whether they're stable or not. But what it does not give us are actual tools by which we say that if a given system is stable or not. So we would generally have a system x dot is f of xt. How do I know if I found a fixed point, if it is stable or not? Do I start integrating trajectories in every and finding for every epsilon a delta ball, which and see that if it is for all possible times staying within that epsilon ball or not? Is hugely inconvenient. You would rather want to have some results or some safe ground based on which you can conclude stability on relatively less computational burden or analytical burden on your side. So this is what this section would be about: stability based on linearization. So once again, we are in the same setting. So x dot is f of xt, and x is an n-dimensional phase space, and f is now once again continuously differentiable, but this time we will be using this differentiability because we would be differentiating the right-hand side to linearize it. And the name kind of gives it away. So can we actually linearize a system and assess and see the stability of the linear system and say something about the nonlinear system? So the question is to have a systematic approach to stability. Of a fixed point. Say the fixed point is, we assume f of pt is 0 for all times. So then this is a fixed point. By the way, there's a side note, which is that it's important that it's true for all times, because oftentimes we find functions which are actually resulting in a 0 right-hand side and claim that there's a time varying fixed point, and that there's nothing, no such thing as a time varying fixed point. So P does not, and this is something that is very common in literature. We see also papers which where they do this and start linearizing their equations on time varying fixed points, and this is something that's actually dangerous to do, and we'll see why just in a few minutes. So P should not depend on time, and actually if there exists, there's a special name for it, if there exists P of t such that f of P of t comma t is 0, so the right hand side is vanishing, then it's known as a stagnation point. I think the terminology comes from fluid mechanics, where you have instantly points of in the velocity field which are changing, and they're instantly having 0 velocity, so that those are points of stagnation and they keep changing. They do exist, but they're not fixed points. And once again, the idea is that we go, so we're trying to find a systematic approach to the stability of a fixed point P, which does not depend on time. It never does. Simple reason, because imagine if you start on it, well, at the next time instant, it's not there. You're moving, so you don't stay there. So the idea, basic idea, is you are probably familiar with of linearization, is that we linearize our right hand side on around the fixed point. So we pass into a new coordinate system. Which are measuring the deviation of our original coordinates from the fixed point P. So this implies that y dot, which is equal to x dot, because P is fixed, there's no P derivative involved here, is nothing but f of P plus y, comma T. This is just x by definition. And now this right-hand side is what we want to Taylor expand. in P, around P. So what we get is f of P comma T plus the Jacobian of f evaluated at P and multiplying by y. And then you would have high order terms here. So this Jacobian itself would be a matrix that is multiplying a vector. Then you would have a 3 tensor, which is also evaluated at P. So this would be a 3D array, which would be acting on the quadratic form y times y. So it's sort of like y, this vectorized version of y squared. And then there would be order y cube terms. So once again, so for us, for the purposes of linearization, this is the term that we are interested in, which is the Jacobian of f. So matrix, how do we evaluate it? Just to recall. Df at P is nothing but the f, the right hand side is an n-dimensional vector. So we take the first component of that vector, f1, take the derivative with respect to the first component in the first coordinate in the phase space, and so on. We keep doing that. We put it in the first position of the matrix of Jacobian. It's an n by n matrix, and then we have f1, and we keep doing that n times for the n coordinates that we have, and then so on. We do that also for the nth component of the vector field, whose derivative we are taking with respect to the first one, and so on to the nth one. Right? And in general, these are of course functions, but we are evaluating each of these functions at the point P, which is fixed. So this would be something that does not depend on space anymore, on X anymore, right? But it would in general, since we were in that setting, it would in general depend on time, right? So let me correct this. This would generally depend on T. And so y is again an n-dimensional vector that is being applied on this matrix. And what we want to do is the basic idea in linearization is to pass into these new coordinates and then only look at the linear part of the vector field after Taylor expanding it. And the idea, and this is where basically this P being a constant, this P being a fixed point and a constant really comes into picture, because this is what we are doing here. You cannot arbitrarily linearize your system around any point. It's this is also something that is done many times in literature. Or let's look at the linearization around this point because it is interesting for us. No, you can only look at linearization around the fixed point. And the reason is because that's where, if we look at the right-hand side, we are ignoring some terms with respect to the others. What is the linearized system? The linearized system would contain only this term. On the right-hand side, we don't know how that term would measure, if it's not a fixed point with respect to this term, with respect to that term, especially if it's a fixed point, we know that this term is vanishing. So this is 0. And if we are near a fixed point, the other terms, which are order y squared, if we are near a fixed point, the deviation, this deviation would be small. So this term would be much smaller in comparison to that term, and only that term matters. So this is actually, this is to begin with 0. This term is small, and that's when we can start to ignore it if you're starting to linearize our system around any point, we don't know what the contribution here is. We don't know how big this is. And so the whole procedure breaks down. So there's a good tradition of really emphasizing this point, that if you see this happening in papers or in anywhere, to realize that this is something that is wrong, and beware of when this is happening, right?
Excuse me, sorry.
Yeah.
So, but in order to be able to write this expression that you're pushing down there, do we implicitly assume that f is analytic in any fixed point? Because if I remember correctly, that's not one of the prerequisites. You only said f is C1.
Yes, you're right. So in principle, when f is C1, I'm not allowed to write. So thanks for that, pointing that out. I'm not allowed to write this. So what I know is that there would be a high order component which would depend on which would be of the order y squared, but it won't be analytic. So we have not assumed analyticity. Not said that this Taylor expansion would be convergent, but we do know that we can write this approximation, right? So thanks for pointing that out. So I'll make this correction. So I would simply write here order y squared, right? Does that answer your question?
Yes, thanks. So yeah, okay. Yeah.
Okay, great. So this would be something which is, now that I've seen the notes, that's how it is as well there. This would be much less than order y when so the idea in linearization is near fixed points pass to the linearized system. Y dot is equal to A of t times y. So A of t is nothing but this Jacobian, where the matrix, which is generally time dependent. And it does not depend on x anymore because we linearized it and substituted the fixed point in it. And our objective is to study stability of the fixed points of this system, of the linearized system, and conclude something about the stability of the original system, that the fixed point P of the original system. So what is the fixed point of this system? It's y equals 0, because we shifted there, and we can see here as well. So the fixed point is y equals 0 of, let's call this linearized system star. So this is one of the objectives. And once we conclude what is the stability of the origin in this linearized system, then we will see what we can say about the stability, what its relevance is to the stability of the original system. It might be the same, sometimes it might not be. So but we'll have conditions under which we can assess the stability of the nonlinear system as well. Right. So in order to study the stability of this linear system, there are some review of linear systems that we would like to do. Basically, and this is something that you've already seen in previous courses on ODEs that you might have taken, but just to make sure that we are on the same page and set up also the notation, we would be doing a little bit of review. So yeah, once again, the system that we're looking at is y dot is a of t. This is a matrix, n by n matrix. Generally, ny is n-dimensional phase space. And we assume that A is continuously depending on time. So again, this is generally a time-dependent system. This is already general enough. This is a linear system, and even in all its generality, this is also still something that we cannot solve. It's constant. When we restrict to constant coefficients, that's when we can actually start doing some business with it. But already at this level of generality, we can apply the tools that we have learned about so far to make some general conclusions, namely. So we know that the system is, of course, Lipschitz continuous globally. So there's actually global existence of solutions in this case. And the solutions are unique. We know that from, so let's call this equation double star. And since it's a linear system, then superposition applies, right? So there's a superposition principle, namely the linear combinations of two solutions is also a solution. So any linear combination of solutions, say if phi1 of t is a solution, and so on up to phi k of t, these are k different solutions, then any linear combination of these solutions is also a solution. This just comes from linearity. We substituted, and we'll see that a linear combination is also satisfying the original equation. Right? So this is something that you already know. We also know that there exists n. If this is an n-dimensional system, then there exist n linearly independent solutions. To its double star, let's call them phi1 of t, so on up to pn of t. And then if we have n linearly independent solutions, then we know we have a vector space, and we can project down any general solution onto these n solutions. So any general solution of this ODE double star can be written as a linear combination of these n linearly independent solutions. So say any solution phi of t can be written as summation j equals 1 to n Cj, which are constants, times phi I of t. These are the independent solutions. So these are all vectors. And these are scalar constants. So which are n-dimensional continuous in time vectors. And finally, I mean, there is a, how can we check? So, I mean, these are vectors which are not just constant vectors, but these are vectors which are varying in time. So this is a big claim that these are linearly independent. If you start with linearly independent vectors, if a solution starts there, then the solution stays linearly independent for all times. And this is something that can be checked. And how do you check that? You take all the vectors and stack them into a matrix. These say they are column vectors, you align them all together, you get a matrix, and you look at the determinant of that matrix. And that matrix has a special name in this constant. It's called, in this context, it's called the Wronskian, denoted by W. So the determinant is called the Wronskian, and so that's a scalar. So that's the determinant of this matrix phi1 of t. So it's a time dependent determinant, so on up to phi n of t. And so for independence, we want that the determinant W of t should be non-zero for all t. Right? And there's actually a result due to Abel, which allows us to conclude linear independence. Okay. And it goes like this. So the determinant at any time t is actually related to the determinant at any time t naught, the initial time, let's say. And this is the relation. You just need to take this exponential of the trace of this matrix A and integrate it. So just take the diagonal elements, sum them up, and this is how we can actually say that if you are starting with a non-zero determinant in the first place, then you would always be non-zero because this is an exponential for over any finite time. This would result in something, this quantity would result in something non-zero. So if W of t0 is non-zero, then W of t would be non-zero for all t. So finally, I would like to also there's a simpler way of rewriting this summation, the general solutions that we're talking about, this one, let's call it triple star, lack of better vocabulary. So this could be represented as a matrix vector product. So we take this matrix of linearly independent solutions and multiply it with a vector containing the constants. So any general solution can be rewritten as a matrix vector product. So y of t, any general solution for double star, is given as p1 of t, so on up to pn of t. The nice thing about linear systems is if you found n linearly independent solutions, you're basically done. You know all possible solutions. So, and this would be the vector of constants. Let's call it C. And this is a matrix. Let's call it psi. And this is usually, so we could write this product as psi of t, right? The same summation that we were looking at earlier. And this is a special name. This matrix of linearly independent solutions is called the fundamental matrix of solutions. And one thing that we can also see is that as a matrix, this also satisfies the original equation, which is y dot is a of t times y. So if we write down psi dot is a of t times psi, this would be true. Now y in general was a vector, but we can also write down each component of this. This is a solution in itself. That would say phi1 dot of phi1 dot is equal to a times phi1, and we can write these n equations and we put them all together in a matrix. So this is like a matrix differential equation that is also satisfied. So for any initial value problem, so how do we find out if we are given n independent solutions? If we are to y dot is a of t times y, say initial condition at t naught is y naught, then y of t is equal to psi, the fundamental matrix of solutions, times c. This would be a general solution. We substitute t equals 0, t equals t naught here. Then we get psi of t naught times c, which must be equal to y naught, which is the initial condition, right? And so this implies that c should be, now psi is an invertible matrix, because remember the Abel's theorem. So psi inverse of t naught times y naught. So this is because columns of psi are linearly independent. and they remain linearly independent because of Abel's theorem. So we can determine C now, and once we have C, we have the general solution at any time t, which is equal in terms of, we again use that relation and now say C of t times C inverse of T naught times Y naught, right? So this is a matrix in itself, and this is something that is unique now because it is taking initial solutions and mapping them to finals, initial condition and mapping it to the final solution. So this is actually a normalized fundamental matrix of solutions. The linearly independent solutions by themselves, you could find any linear set of linearly independent solutions. They need not be unique. They may vary up to constants, but the moment you normalize it like this becomes a unique matrix, which is known as the normalized fundamental matrix of solutions. And what should necessarily hold true is that if I take phi t naught to t naught, that is equal to identity. That's true here itself. We see it here, but because of this is what really leads to this terminology that it's normalized in that sense. So this is unique. And aside from that, there is one more thing, we are talking about general linear systems here, but in the context of systems which are obtained as a linearization of a system, in the sense that if A of t is the linearization of some right-hand side, nonlinear right-hand side, then it turns out, and this is something that you can check, that this normalized fundamental matrix of solutions T naught to T is nothing but the deformation gradient that we've been looking at. And this is an exercise. So this is pretty much where we would need to, what we can say about general linear systems where we have time-dependent coefficient matrices. And this is where we would like to actually restrict our discussion. We already know a lot about general systems. We thought it's good to recall that in this generality that we have n linearly independent solutions, and we can have this kind of a setup. But this is pretty much what we can say. As much as we would like, we still are not able to solve these systems explicitly. There are systems with constant coefficients which we would be able to explicitly solve, and that's what we would like to restrict to next. But I hope this was a useful review, and then once we restrict to that, that's where we would be able to see how we can assess the stability of the fixed point. This is just in some sense setup. Sorry. So we now restrict our discussion to autonomous case. So y dot is ay now. So in particular, ddt of a is 0 for all times. And in this case, we actually do have an explicit solution, and we know it as the matrix exponential. And so we can actually compute this normalized fundamental matrix of solutions. And now we're going to restrict to the case when T naught is 0 because it's an autonomous system. Remember, it does not matter anymore what T naught is. So we can just say that it's phi of capital phi of T, where T naught is implicitly assumed to be 0, or I will write it as a function of T, right? Which is defined as capital phi from 0 to T, and capital phi of T is actually, this is something we already know from linear systems, it's constant times e to the at. And as much as we'd like to write that integral of e to the integral a of t as a solution to the previous case where e of a was time dependent, that does not hold true, and we'll see that. And so what is the definition of this matrix exponential? Exponential is an analytic function. We write down its Taylor series, and we put so the exponent matrix as an argument then, right? So at would be an argument. So this would be 1 over j factorial times at to the power of j, right? So how do we, so this is a solution, and we can also check that it's a solution. So what is, so how do we check if it's a solution? We should have, it should satisfy, as we saw, any fundamental matrix of solution must satisfy the matrix differential equation. So this should also satisfy phi dot is equal to a phi. So let's quickly compute what phi dot is. How do we do that? We look at this definition here, and we take the time derivative. So this is the summation, take the time derivative inside, 1 over j factorial ddt of at to the j. I mean, I'm sure you can do this, but there's a point that I want to make based on this. That's why I'm carrying this out, which is j. So what we would get inside is that a j would come out and it would knock off with the j factorial. So we would have j minus 1 factorial. And there's a constant term identity with which vanishes. So we write this summation from 1 to infinity instead of 0 to infinity. And then we have the power, which would be j minus 1. And then we have to, by the chain rule, we have to write down the derivative of at with respect to time, which would be just a. Right? And now you can see that this works because any power of a basically commutes with it. So what we are looking for is a in front of phi. So we can take this a inside, make it a to the j again, and then this is an infinite summation, take an a outside, and this is what we would get. And also what we see here, that this is a summation from j equals 1 now, but we can basically, and we have j minus 1 power as well as j minus 1 factorial. So we can make this summation from j equals 0 to infinity and write a j here instead of j minus 1, right? So that's what we're gonna do, and make this a go here. So any power of a commutes with itself, right? So we can write a to the j minus 1 times a as a times a to the j minus 1. So we get j equals 0 to infinity, a2 to the j, which is nothing but, again, use the matrix, the definition of matrix exponential, which is a times. So this is how we are able to check that this is indeed a solution. And I think I'm kind of running out of time, but I wanted to quickly make an side note, which I was alluding to earlier, which is that phi t naught to t, if you try to say that based on this analysis, if we try to guess that the integral t naught to t a of s ds is a solution to the non-autonomous case, that would be a mistake. And this is also something that is commonly observed, and sometimes it's true, and we'll see a couple of cases when it's true also, but this is not a solution to y dot is aty. And indeed, if you check this, so it seems that I'm already 5 minutes past time. So I think we will check this next time. But generally, the reasoning behind this is precisely what I was saying, that because a commutes with any power of itself, it actually does not commute with an integral of itself. So that's the reason we end up not having this as a solution. There are cases though where it is a solution, and that would be precisely the case when the integral commutes with the matrix, and we will see that next time. But just to summarize, this was the idea here, is that we want to review linear systems, and if we can write down explicit solutions to linear systems, which is what we are trying to do here, we will be able to assess the stability of the fixed point, which is the unique fixed point origin in this case, and further on we will go on to make a relevance of that stability to what it means for the original system that we wanted to study. So I would be staying on for questions. Thanks a lot for bearing with me in this week. Next week, Professor Haller would be back and continuing it from this point. And I look forward to seeing you in the problem sessions. If there are any questions, please go ahead. Okay, thanks a lot. Okay, thank you, welcome.
I'd have a small question, whether you could go back a bit to the initial value problem that you described, because I think I missed something or I got distracted.
Sure.
Where you described, yeah. Got a few problems. First, where you wrote columns of psi are linearly independent. I'm confused how psi equal, psi t0 c equal y0 equals c, and then we got the inverse. Is it an equal or a implication sign?
I did not mean to do that. Yeah, this is an thanks
Like
a lot
right
for catching that. Yeah, this is a very thanks for catching that. So this implies that indeed C is C inverse that. And what I wanted to put an arrow towards is this equality, because we are inverting C of T naught here. Right, and we can invert it because its columns are linearly independent.
Yeah, that makes it
right.
And then the line, where is it? The line below that y of t is equal to psi of t. Could there be missing a c there?
Indeed, yeah. Wow,
Okay.
I can't believe how sloppy I've been. I think these notes would require a view before they get posted. Thanks a lot.
Okay.
I'm glad that someone was paying attention.
I mean, I guess it was kind of obvious for the others who were listening. I got distracted, so then I got confused by the notation.
No, this is very much appreciated. So it would have been great.
The normalized fundamental matrix would then be from T0 to T.
Yeah, you're right.
Okay.
Wow.
That's it.
Really in a hurry. So yeah, you're right. And so this should be T0 to T. Okay. Wow, these are very, very valuable typos that you caught in this. I don't know, it was clearly not making sense without this. But I'm really glad that you corrected me here. So my apologies if there were any confusions because of this, and thanks to Simon for catching it.
Thank you a lot.
And
then
you're welcome.
See you next week, I guess.
See you next week. Okay. All right, if there are no more questions, then see you next week. Thanks a lot.